All right, so let's look at some elimination mechanisms, and let's specifically look at the E2 mechanism. Certainly one of the more difficult aspects of E2 is there's a geometrical requirement that's absolute and must be present, or the E2 mechanism simply isn't possible. And that's an anti-periplanar arrangement of the two atoms I'm going to remove from the molecule. So remember, we're going to have 4 atoms in the mechanism. We're going to have vicinal carbons. There's going to be a leaving group, which I'm going to represent with X. And there's going to be a hydrogen that I remove. Remember, mechanistically, we're going to have a proton transfer. And then we're going to have loss of a leaving group. Now in E2, this is going to happen in a nearly simultaneous fashion. When you're confronted with a molecule, however, you got to put it in a conformation where you can be absolutely certain that the leaving group and the hydrogen you're going to remove are anti. And this usually means drawing a Newman projection. So we have a fairly complicated molecule here. So it has 1, 2, 3, 4, 5, 6 carbons in the longest chain. But to simplify things a bit, we're going to look down the bond of this carbon and this carbon. We have to do that because there's only one good leaving group in the molecule, that's the iodine atom. This beta carbon does not have a hydrogen, so there's no elimination product. So we have to remove the hydrogen from this particular carbon. So we're going to look down with our eye down this bond. So this will be the front carbon in the Newman projection. This will be the reverse carbon in the Newman projection. We haven't talked about this in a while. But if I rotate this, in your mind's eye, you need to realize that the iodine is going to be positioned down and to the right. The hydrogen will be down and to the left. And of course, the T-butyl group is going to be in the same plane. That takes care of the front carbon. Now for the back carbon, when I make this rotation, certainly the methyl group is going to be in the same plane. And as I look down this bond, and this is not necessarily easy to see, the ethyl group is going to be up and to the right, and the hydrogen is going to be up and to the left. Now the question is, what is the relationship between the hydrogen that we're going to remove and the iodine that must leave the molecule? If you look at the Newman projection, they appear to be anti. So I would take one last look at this to ensure that these molecules, when I've made this transformation to the Newman projection, it's correct, and it looks to be correct. So when the base is utilized in this reaction, we remove this hydrogen. We're going to make a double bond, and this is a little tricky to analyze, and this iodine is going to leave. This is going to leave us with a carbon-carbon double bond. On the back carbon, what we are left with is a methyl group and an ethyl group. So here's the methyl on the back carbon, here's the ethyl on the back carbon. So in no particular order, I'm just going to place the ethyl and the methyl on the back carbon. Now on the front carbon, I have a T-butyl group and I have a hydrogen. So notice that the T-butyl group and the ethyl group are gauche. When they are gauche in the Newman projection, they will be on the same side in the double bond that I make. So I will put the T-butyl group on the same side, and the hydrogen will be trans-like to ethyl because in the Newman projection it is anti to ethyl. This, of course, gives us a Z-alkene. We will not get a mixture of E and Z in this reaction. It is stereospecific. Sometimes we'll get the cis-alkene, sometimes we'll get the trans-alkene. So this reaction is unique in that it can give a less thermodynamically stable alkene in a 100% yield. So we have another example, and in this one I'm going to call this carbon that I've rendered in blue the front carbon, and this carbon in magenta the back carbon. So when I look down this bond axis, what we should see on the front carbon the ethyl group is in the plane, and we should see the methyl group up and to the right. Hydrogen up and to the left. And you know, people of varying skill levels can see this better than others. But if you put yourself above the plane of that molecule, I think you can see that the methyl is up and to the right, the hydrogen is up and to the left, and the ethyl is straight down. Now, the back carbon. Don't judge my circles. So the cyclopentyl group is in the plane. So I'm simply going to cyclopentyl group in the plane. And of course, the bromine now is going to be down and to the left. While the hydrogen is going to be down and to the right. Now, in an entirely separate color, we'll use orange. I know that the bromine has to be my leaving group. So this has to leave. And the hydrogen on the beta carbon must be removed, which is this hydrogen that's rendered in blue. Notice that that hydrogen and that leaving group are gauche to one another. They're not anti-periplanar. So what I need to do to get them anti-periplanar, I'm going to hold the front carbon steady, and I'm going to rotate the back carbon 120 degrees counterclockwise. So when I do this, the methyl group stays where it is. Hydrogen stays where it is. Ethyl stays where it is. But now the bromine is down and to the right. And now the cyclopentyl group is down and to the left. And the hydrogen straight up. So now the hydrogen that I'm going to remove and the bromine that must leave is now anti-periplanar. So I can push my arrow in this Newman projection. Again, this arrow is going such that the carbon-carbon double bond is actually going into the plane of the screen. So you can't necessarily draw that easily. And the bromine, of course, or the bromide is going to leave. So what I'm going to do is I'm going to draw the carbon-carbon double bond. On the back carbon, I am left with cyclopentyl, and I'm left with hydrogen. So in no particular order, I'm going to render that. Now, cyclopentyl is gauche with the ethyl group, which means the cyclopentyl and the ethyl group need to be trans. Excuse me, I messed that up. Not trans, they need to be cis. If they were anti, they would be trans. So once again, they are gauche. These two groups are gauche. They are on adjacent carbons. Gauche equals cis when I'm translating this Newman projection. Which means the methyl group, notice the methyl group is trans relative to the cyclopentyl group. So it's trans-like. The high priority, of course, on this carbon it's cyclopentyl, on this carbon it's ethyl. This means I get a Z alkene. Now that's not the only alkene I can get, because I also have a hydrogen right here. And that would be an entirely different Newman projection analysis. But you see how you go through the steps to justify the major product with regard to removing a hydrogen from, if you will, the blue carbon, as opposed to, I guess we can call this the green carbon. And you would do the same thing again. You will have to do this on your final examination, so it's a worthwhile skill to practice. Translating it to a Newman, doing the proper rotation, predicting the major alkene that's going to result.